Good day, everyone. In this lecture, we'll consider impulse response and convolution of the LTI systems. So let us begin. You'll recall that an LTI system fed with an input, say S of t, is LTI characterized by system property H of t, will produce an output Y of t, given that S of t involves with H of t. Now, H of t is the impulse response of the system. It is a property that characterizes the system. And for ease of analysis, H of t is easier to evaluate in the frequency domain. And hence, should we take the transform of H of t and get H of s, which is a frequency domain representation. So H of s, therefore, is the system function of the LTI system. Let us still transfer function. So, a tool for this transformation is referred to as the Laplace transform. Which we'll cover in the lecture. Okay. So, what is the system function? So, now that we have the system defined as this LTI H of t and Y of t, should we take the Laplace transform of S of t, then we're going to get S of s. The Laplace transform of H of t will get H of s. Laplace transform of Y of t will get Y of x. What we are saying here is that the system function H of s is the ratio of the Laplace transform of the output Y of x to the Laplace transform of the input, considering the fact that all initial conditions are set to 0. So 0 initial conditions. So simply put, the system function, or better still the transfer function, is the ratio of that transform transform the input, all the initial conditions set to 0. Conditions to be 0. Okay. And in our previous lecture, we established that for any given linear system, if the input is 0, then the output will be 0. Otherwise, the system is not linear. So the total solution, the total output of the system is the same as the sum of the 0 impulse response and the 0 state response. For the 0 response here, we have input to be 0, and for the 0 state response, we have the input to be applied. So, and the ZR is the response due to the initial conditions, while the ZSR is the response estimated when it's applied. Well, we covered that in our previous lecture, just trying to review that. So, now, in the time domain, what is the impulse response? Now that we understand that the frequency domain representation enables the evaluation of the system function, having taken the Laplace transform by transforming from the time domain to the frequency domain, but you'll see that the impulse response itself is defined as the output of an LTI system when the input is a unit impulse. That is, given that the system is fed by a unit impulse, LTI system, then the output is the same as the impulse response. And you will recall that a unit impulse has an infinite amplitude and a finite area, largely because it only exists around the time scale t equal to 0. That is, direct delta function is defined to the infinity at t in the same as 0 and the 0 otherwise. So, in other words, we have it existing this point. Okay. So how is that? Let's try to show you the proof. So let's assume y of t is given as 2a for values ranging from A to A, 0, guys. You see that we have a rectangular waveform. It looks something like this. Say minus A to A. This is y of t. This is t. Now, if we estimate the area under this graph, we take the integral from negative infinity to infinity y of t dt. So the limit here is minus a to a. So we have minus a to a dt, 2a t minus a to a. Then this will be the same as 1 over 2a to a minus minus a. It will be the same thing as 1 over 2a 2A, so this is the same as 1. So it means the area under this graph is unity. And now you realize that as the width of the area reduces, the height is seen to extend towards infinity. So let's assume this part now on the red is reduced by half, say minus A2, A over 2, such that we equally get an area, a unity area, in this case. So it means that y of t in this case is defined as 1 over a, taking values from minus a over 2, let's go to t, let's go a over 2, and 0 otherwise. Now, the area, in this case, taking the integral from minus a over 2 to a over 2, 1 over a t, that will give us a t, so 2, a over 2, so a, a over 2, minus a over 2. This gives us a, which is equal to. So, technically, we can conclude that as the height tends to 0, as the width tends to 0 rather, the height is seen to extend to infinity. Okay? Seen to extend to infinity. 0. Okay? Such that the area is defined as 1. Therefore, maintain a unity area, the height seen to extend to infinity as the width reduces to 0. So this brings us to the conclusion. This is where 1 is the area. See? Where 1 is the area units. Okay, perfect. Now, recall that we already defined the impulse response as the output of the LTI system when the input is the unit impulse. So therefore, should the unit impulse response be scaled by some parameter k, say k, then So y is the same as this, then the area will be seen to be scaled as well. Now let us look at this. And the area will be the same. It's negative infinity to infinity, y of t, which is now infinity to infinity, k dt, delta t dt, same as k, to infinity to t. And now we already established that this extends to unity, so it means k times 1 is the same as k, such that the output therefore something like this. Now, since u of t step response, unit step response is same as 1, then the area, which is the same as this, delta dt, the same as 1, the same as u of t. So hence, the integral of the unit impulse is the same as the unit step function. So, we can therefore mention here that the first derivative of the unit impulse is the same as the doublet. Okay? And this is referred to as the doublet function, such that d dt unit impulse same as the doublet. But when the unit impulse function is time shifted, then the Dirac delta is seen to be shifted to the time of interest. This is what we mean. There are a few properties. So this is the area. See? Now, if we perform time shifting here, such that this t sub k, see that the unit impulse is shifted to the time of interest, t sub k. As this parameter is very useful when we talk about something. Okay. So when the signal s of t is multiplied by the time shifted unit impulse response, say s of t is multiplied by the time shifted impulse response, then the signal is seen to be shifted by the time t sub k, such that the signal therefore assumes its value at this time t sub k, that is t sub k. Now, the signal s of t, the time t, is now seen to assume the value t sub k. Now, as this has been defined to have an area of 1, then to be logical to conclude that S of t sub k times 1 is the same as S of t sub k. And it is logical to therefore conclude that should we have a signal, say something like this, multiplied by some time shifted unit impulse, say t sub 1, t sub 2, t sub 3, t sub 4, t minus t sub k, this is S of t, this is t, this is 0, this is 0, this is t. Then we are going to get something that looks like this. It's 1, 2, 3, 4. S of t. This okay. 2. So this t sub 1, t sub 2, t sub 3, t sub 4. So this is therefore equivalent to S of t sub k this is t sub 1, t sub 2, t sub 3, t sub 4, this is t, which is the same as y of t. Okay, given that y of t is the same as this. Now, so it is observed, or can be observed from this, that S t sub k by way of expansion can deduce that S t sub 1 is the same as S of t sub 1, that's t minus t sub 1, S of t sub 2, same as S of t sub 2, that's t minus t sub 2, S of t sub 3, same as S of t sub 3, that's t minus t sub 3, S of t sub 4, same as S of t sub 4, that's t minus t sub 4. Okay. Now, since the signal S of t could be disintegrated, now you see that the signal S of t, now has been disintegrated into a set of impulses. So, separate impulses, right? Into a set of impulses. 1, 2, 3, 4 impulses. Therefore, the response of the LTI system is therefore seen as an arbitrary input signal, which is the sum of the scaled and shifted impulses. So from this, you can see that since the signal S of t, this integrated to set impulses, so S of t sub 1, S of t sub 2, S of t sub 3, S 1, 2, 3, 4, S 1, 2, 4, S of t sub 4, response the LTI system Neutral input signal, simply the sum of scaled and shifted impulses. Okay, so we can conclude from this deduction that y of t is the same as s of t sub 1 plus s of t sub 2 plus s of t sub 3 plus s of t sub 4 from this expression. Okay, and this therefore is the same as taking the integral from t sub 1 to t sub 4 for s of t sub k and then this is t sub k after the multiplication dot time shifted impulse dt. Now this expression is referred to as the convolution in the time domain. Hence, the convolution is the sum of the scaled and shifted component. Now, this is scaled and this is a shifted component. Okay? This is the scaled component. Then this is the shifted. So, we can therefore generalize based on these deductions. General any continuous time signal is the sum of the scaled and shifted unit impulses. Given as t, same as integral from infinity, positive infinity, is of tau, t minus tau, the tau. Now, where is of tau is a scaled component, t minus tau is a shifted component. Now, similarly, in the discrete time version, or that's the discrete time version of the continuous time signal, we can also define this as follows. So, similarly, any discrete time signal is a sum of the scaled, shifted unit impulses given as of n, the sum k, taking on values from infinity to infinity, is of k minus k. Now, same way here, s of k is a scaled component. Y delta n minus k is a shifted component. Good. Since the impulse response h of t or h of n is the output of an LTI system, just as we defined earlier, when the input is a unit impulse, so it's delta t or delta n is therefore sufficient to completely characterize a system. This T goes into a continuous time LTI system, CT LTI system, H of T, and goes into discrete time LTI system, get H of N. So once the impulse response is known, then the system's response to any input can be evaluated by convolution. So this. So for a continuous time system, split this. So T into the LTI system, so like this. T such that T same as S of T involved with H of T. Then the continuous time convolution integral is given, right? T same as integral so tau H of T is tau d tau. While for the discrete time system of n for the LTI system. Okay. N is the same as S of n for H of n. Then discrete times sum is given by n the same. Okay, taking on values from infinity to infinity. Okay, H of n scale. So here you will note that convolution produces an output that is the sum of the scaled and shifted impulse responses. Okay, so we have the scaled, we have the shifted response. Okay, scaled, shifted response here. So okay, the scaled and shifted response here. So let us consider a few steps. Steps required for convolution. So the first point here is the impulse response. H of tau is time reversed. So impulse response H of tau is time reversed. To obtain H of minus tau. So this it is reflected about the time scale. Okay, so the next is to perform time shifting on the time reversed signal. So from time shifting of star to obtain H minus times T should give us minus x minus then minus times minus plus. So that will give us H of T star. Okay. Afterwards, third point is to multiply the signal of tau star for all tau T fixed at some value. Okay, then we integrate the product. For tau. Now And this is done to produce a single output of t. So, single output t. Then the final step is to repeat 1 through 4. Over the time interval from negative infinity to positive infinity to obtain the output. To obtain time. Okay, let's consider one quick example. Split board. So let's assume we are given s of t to be a unit step function, and then h of t to be the same as epsilon minus at u of t for values of a greater than 0. Now, if we assume a system that looks like this, h of t, then this is y of t, then we can conclude that y of t is the same as s of t convolved with h of t, which is the same, this continuous time signal, which is the same as the integral, taking limits from negative infinity to positive infinity, x of tau, h of t minus tau, d tau. So, can therefore conclude that s of tau, given s of t to be u of t, then s of tau will be the same as u of tau. Similar vein, h of tau will replace t by tau, be the same as epsilon minus a tau, u of tau. Okay. So the first thing to be done is to represent the signal. So let us do that graphically. So we have unit. So this is s of t. No, sorry, s of tau. This is s of tau in the same as u of tau. Okay. Now h of tau is given such that h of tau, note that h of tau is the same as epsilon minus a tau, u of tau. So it means that the part of the signal at this extreme will be truncated because only the part multiplied by the unit step function will be realized or will be achieved or seen after this product. Okay, we already explained that in our previous lecture series. So at this point, we look at something like this. It's not. Okay, let's change the color. So there's something like this. So the next thing to do is to obtain the time reverse version. So h of minus tau, and that's as good as flipping about the time scale axis. This time scale axis here, time scale axis. So if we flip about the time scale axis, so something like this. Unity, right? Now, if we do this, means what we now have here is h of minus tau epsilon x a to tau u tau. So it means the unit step function also flips, so we're able to see the signal on this other half, right? This part is truncated. Okay. Now, the next thing to do here is to investigate, or better still solve for the time shifted version. That would be h of minus s. Use different, let's use braces. Minus tau, that's tau, right? Tau c so it's been shifted by t. Okay, this is so the implication here is that h of minus tau minus t is the same as a minus tau minus t u of minus tau t. So if we expand this, so what we have here is the same as h of t star because this point minus times minus, that will be h of minus tau minus times plus plus t epsilon minus a minus tau plus t tau plus t, which will give us h of t minus tau is minus epsilon minus a t minus tau u of t plus tau. So here we have h of t minus tau same as epsilon a t minus tau t minus tau. Okay, so now we want to take the product of this product of this and this as our output. So we have y of t, which is the same as s tau involved with h of s of t convolved with h of t. So what we have here is this 0, this is 1 anyway, this is t, and this is 1 times t, this is 0. So at this point we see that y of t is the same as s of t convolved with h of t for t less than 0. And you see that the values of the shifted component and the values of the scaled component don't coincide. Hence, by multiplying each component by each component, y of t will be equal to 0. Okay? So, let's now consider y of t at t greater than 0. Because here, t in this case is less than 0. Okay? Now, if t is greater than 0, then it means this shifted component is moved to the right, towards the right, more like sliding towards the right. So once we do that, see y of t now looks something like this. See? So in this case, see that this component is the same. Okay? What do we do? So at t greater than 0, y of t, we now take on values from 0 to t, integral 0 to t, epsilon a t minus tau. This is neutral. Okay? Let's move to the right. Okay? So 1 times this is this. Now, time we integrate this, we're going to get 0 to t, so it's 80. Let us expand this. So a times t, a plus times this, a tau, this is tau, a tau. So this is a constant, so that will go in, so t to 80 integral 0 to t, so tau. This equals epsilon 80. I can integrate this divided by a tau 0 to t equals 80 A T 20. Okay. So now this expression is going to tend to 1, right? So that we have here is 82 T 1, which is now, sorry, A, it's 2. This is A over A, it's 2. It's now the same as 1. A, this times this, and this times this, that's 80, 80, which is the same thing as A, B, A plus A, T, T, okay? So this will be the same thing as 1. A, so 0, that's minus A plus A 0, 0 times T, epsilon naught, times T, which is the same thing, so this reduces to 1. A, so this point, therefore conclude that phi of T, same thing, 0 for T, that's 0, this is 1 by A, and epsilon is 80, T greater than 0. Simple. Okay, so let us consider the example. So example 2. Let us show, that's right, show that convolution two rectangular forces of equal postulation to produce a triangular. Okay, we'll run through this quickly. So let's assume that this function something this is 0 naught 1 is duration t second. Let's assume the sigma t amplitude here is a second. So this converges to the sigma having the same duration but not necessarily the same amplitude. T sub 2 is 2, then S2 T. So here we want to prove that this is going to give us a triangular function. But here, you should note that equal cos duration in this case implies that T1 is the same as T sub 2, so we can say the same as T. Okay? Meaning not 1 is the same as not 2, is the same as north, because that is the origin. Okay, so we have equal duration because this time period is the same. This is A2. This is the amplitude of second signal. So if this is a triangular signal, how do we construct this? So at this point of at this origin, let's do something different. Let us write this to make it let's make it colorful. Let's say this is x1, this is x2, then on this side, let's give it some other color. Let's say t sub 1, t sub 2. Let's leave it. So it means that at the point of origin, I have to add not 1 plus not 2, which would be equal to 0. Okay? Now, we're going to be having the center point. Okay? And then the equidistant point. Okay. Now, at this point, so if you trace this down, okay, this equidistant location, this distance is the same as t. Recall that t1 is the same as t2, so it's the same. Okay, that's t. Such that this location here will now give us t sub 1 plus t sub 2. And we know they are equal, so it's the same as t plus t, which is the same thing as 2t, right? At this point. Then, the apex point, which is going to take on value at this point, this is going to be the product of A1, this amplitude, times this amplitude, A2, times the time duration, t. So afterwards, join these points. That's simple. Okay, let's look at one more example. Let us show the convolution of two rectangular pulses of an equal course duration to produce a trapezoid function. So let's assume we have function involving with a function, different duration. So this is S1 of t, this is S2 of t, this is phi 1, this is t sub 1, this is phi 2, This is t sub 2. So in this case, note that t1 is not the same as t2, and that t1 is less than t2. Okay, so the convolution process here will result in a trapezoid. So for us to construct that, we're going to have something like this. So at the point, at the origin, we have phi 1 plus phi 2, right? Then we're going to have about 3 locations here of interest. Okay, so what are the first, which is the origin, the first, second, third, and fourth point. So in other words, from the origin, when we investigate this, so how do we calculate for this? And then also from the origin, I'm going to tell this distance. So from the origin, this is the shorter duration, which is T1. And this other point is the larger duration, T sub 2. While this third point here is the sum of both durations, T1 plus T2. And then the amplitude value, which is somewhere between this point and this point, is going to be A1 times A2 times T1. Recall that T1 is the smaller duration. Okay? So once that is done, join the points. This is that. Yeah, this is half T. That's simple. So let us consider some of the basic properties of convolution. So the first is associative property. And here, say that when S1 of t convolves H1 of t, and both the outcome convolves with H2 of t to be the same as S of t convolving with the outcome of H1 of t with H2 of t. The second property is distributive. So in this case, we have S of t involving the sum of H1 of t plus H2 of t to be the same as S of t convolving with H1 of t plus S of t convolving with H2 of t. So S of t convolving with H1 of t plus S of t convolving with H2 of t. The third property is additive property. So in this case, S of t involved with H of t is the same as h of t convolved with x of t. And then we have the linearity property, like we established in our previous lecture. To be worth mentioning at this point that convolution is a linear operator, okay? Such that any linear operation on the output, albeit as still input, which is vice versa, will result in an equivalent operation at the output. So if we take, for instance, time derivative of h of t will result in the time derivative of the output. Okay, we also have time invariance, such that any time shift, either s of t or h of t, will result in an equivalent shift in the output. So in other words, what we're trying to say here is that delaying the input will delay the output by the same amount. Delay output, same and one more point to note is that, let's say what is the sixth point? Convolution in time is the same as multiplication in frequency. Okay, so it means that y of t same as s of t convolved with h of t in the time domain. So once we move to the frequency domain, it becomes y of s equal to s of s, h of s. Okay, so it means that evolution time is the same as multiplication in frequency. So when we move from the time domain to the frequency domain, say via Laplace transform technique, so Laplace transform, technique, what we end up doing, the convolution equivalent in the frequency domain becomes multiplication. So we rather multiply these parameters. Why, if we take the inverse Laplace transform, the inverse Laplace transform, coming back this way, from the frequency to the time domain, then it is convolution time. Perfect. Now we've considered a few continuous time convolution examples. Let us check out, say, one example of discrete time convolution. Okay, so given that, so this is discrete time convolution example. So let us say, okay, let's break this into okay. So let's assume we are given S of n to look something like this. This is 0, this is 1, this is 2. Call for the discrete time signals. They are identified by their magnitude. We call our first lecture. This is 1, this is 2. And then h of n is given as well, we are not drawing to precision anyway, but I hope you get the concept. So this is n. So this is 0, 1, 2, 3. Good. So if we assume a system of the form S of n is into h of n, then we get y of n, then we can conclude that y of n is the same as the sum k equal to infinity to infinity s of k and h of minus k. This is the same as k being the same as negative infinity to infinity s of k h minus k minus n. So it's about the same. So as minus times minus is plus n minus k. Okay. So this also is going to give us the same as let's say summation here s of k h of minus k is k from negative infinity to infinity, so it's the same as summation here k from negative infinity to infinity s of k minus n. Let's assume we subtract n from both the scaled and shifted component, then this will be the same as h n minus k minus n, isn't it? So minus n here, minus n. So this is going to give us something that looks like this. Okay, infinity to infinity. So k minus n h, so n minus n, so we leave us with minus k. Just about the same thing. So at this point, we can actually play with y of n is the same summation k equal to negative infinity to infinity, so k minus n minus k. Perfect. So if we assume that n, if we replace n with k, let's assume such that x of k will now be the same as what we have here. So let us redraw this. This is 0, 1, 2. So that is minus 1 magnitude. It's magnitude of 1. It's magnitude of 2. Then h of k here. Is the magnitude 4 now. This is 0. This is 1. This is 4. This is 2, right? Then this is 4. This is 1. So this is 2. So now I have replaced n by k. So this is k. But from our analysis, we need the time scaled version. So the time scale version here will be h of minus k. And this is going to give us something like this. And then this is 0, 1, 2, 3. So minus 3, minus 2, minus 1, 0. So it means that minus 3 this time, minus 2, minus 1, 0. So minus 3 now is 2, minus 1 now is 4, 1, minus 1 rather, is 1, then we have 0. Good. Now that we have achieved this, we can begin our analysis by using the deduction here. So at n equal to 0, for instance, at n equal to 0, so this expression will become y 0. So when n is replaced by 0, that will be the same as s of k times h of minus k. Now we already have x of k here, we have this here. So if we redraw this, we're going to have something like this. We already have this is 1, this is 2, this is minus 1, this is 0, 0.1 and 2, and this is going to k. Okay, so this is going to multiply the time scale function, which is 3 minus 2 and this is minus 1, 0. This is 2, 4. So you see that at 0, this is 0. We have a value that overlaps. So what we want to do, multiply values that overlap. Okay? So the implication here is that what we want to do, we want to multiply values that overlap and as well add the resultant values. Okay, so that's what I want to do. So in this case, 0 at point 0, the magnitude here is 1. So y of 0 is equal to 1 times this 0, this point 0, plus at point 1, there's no point 1 here, so there is no overlap, so it's 1 times 0, right? Then at point 2, that's minus 1, sorry. The magnitude is minus 1 times 0 because no overlap. And at point 2, it is 2, there's no overlap too, so it's 2 times 0. No overlap meaning the time scale here does not have 2, does not have 1. It only has 0, minus 1, minus 2, minus 3. So the time scale here that coincides, this minus, okay, that coincides with x of k is 0. Only point 0 coincides. We have point 0 here, we have point 0 here. And the magnitude of point 0 here is 1, which is 1. The magnitude of point 0 here is 0. So in other words, at these 2 points, there is no overlap, right? No overlap. So 1 times 0 is equal to 0. So y of 0 is equal to 0. So let's take note of that. So I'm going to repeat this process for subsequent points till there is no overlap. And then we add up the entire process and that will be it. So let us take the next example. So let us, not the next example, but the next point. So let's say when n is the same as 1, so y of 1 will be substituting into this, so that will be n is the same as 1, so that will be k minus 1. So k minus 1 times h of minus k. Okay, so this case now, let us draw s of k minus 1. For s of k minus 1, this is k. 0 minus 1 is minus 1, minus 2, minus 3, right? So we're going to be having 0 minus 1 is minus 1, 1 minus 1. So when k is 0 at this point, so that will be minus 1. 1 minus 1 is 0. So at this point, minus 1, this is 0. And at this point, this is 1. Then at this point, which is k, is k minus 1. So 2 minus 1 is 1. So at this point, which is 1, we have 0.2. This is k minus 1, right? Now, I'm going to multiply it with what we already have here. That's minus k. So we have 2 for minus 3. We have 4 for minus 2. This is 2. We have 1 4 minus 1, then 0 for 0. So the points that coincide or better still overlap, in this case, minus 1 and 0 overlap, okay? So we don't have 1 here. So at point minus 1, we have 1 times 1 here, minus 1 here is 1, plus at point 0, we have minus 1, times at point 0, we have 0. So at point 0, at point 1, we have 2, but there is no overlap here, so it's 0 here. So in this case, no overlap, right? Perfect. So this is equal to 0. So, no, not equal to 0, please. So that will be 1 times 1 is 1, plus 0, minus 1 times 0 is 0, plus 0, which is equal to 1. So y of 1 is equal to. Okay. So I'm going to wipe this part, then while we solve for the others. Okay, so we'll continue from where we stopped here. And you see that at n being the same as 2, then y of 2 will be the same as s of k minus 2, h of minus k. So we already have this in place. So this is minus 2, minus 1, 0. So at this point, minus 2, minus 1, and 0 coincides exactly at this point. Okay, let's change the color. All of these points coincides with these points. So at minus 2, that's 1 times 4, plus at minus 1 times 1, then at 0, 2 times 0. So that'll be 4 minus 1, that's 3. So at n being the same as 3, so we have s of k minus 3, h of minus k. So this is minus 3 minus 2 minus 1. And then you see that minus 3 minus 2 minus 1 coincides with minus 3 minus 2 minus 1. So there's an overlap there. So at minus 3, it is 1. 1 times 2 is 1 times 2. Then at minus 2, it is 4 times minus 1. And then at minus 1, it is 2 times 1. So that will be 2 minus 4 plus 2, which is the same as 0. So at n being the same as 4, so we have y4 is the same as s of k minus 4 and h of minus k. So h of minus k is already established there. So this will be minus 4 minus 3 minus 2. So you see that minus 4 doesn't overlap. So we only have minus 3 and minus 2. So 1 times 0 because it doesn't overlap. Then minus 1, which is at point 3, times 2, plus minus 2, which is magnitude of 2, times 4. That will be minus 2 plus 8, which is 6. So at point n equal to 5, so we have s of k minus 5, h minus k. So that's minus 5 minus 4 minus 3. Now you see that minus 5 minus 4 doesn't coincide. So only minus 3 coincides, which is 2 times 2, which gives us 4. And now, should we increase n beyond 5, you see that there will be no overlap because we are going to be having minus 6, minus 5, minus 4, and there won't be overlap, so it will all be 0. So I think that's a good place to stop then. So you see that by inspection that y of n is the same as when y of naught, that's at 0, is 0. So we have an arrow pointing to show that starts from the origin. Then we have 1. Then we have 2, it's 3, 3, 0, 0.4 is 6, and 0.5 is 4. So this gives us a discrete time sum or convolution. So how will the output look like? So let us wipe this part of the board. So the output is the same as this. So the arrow pointing at the origin, so that is 0. We have 1 at 0.1, 0.2, 0.3, 0.4. Okay, so this is 0, 1, 2, 3. 0, 1, 2, 3, 4, 5. So the convolution of these discrete signals will generate this output following the steps. So hence, S of n convolve with H of n will give us Y. Just before we wrap up this lecture, note that deconvolution is the process of recovering the input signal given the output signal. So recall that convolution itself is used to derive the output given the input signal. So the reverse process gives us the deconvolution. Covering signal in the system. So technically, we say it is the inverse of convolution. Okay. Then, if we have a system, say S of t, for which h of t gives us the output, should the output y of t gives us a response h hat of t, and then we are able to generate S of t. You will observe that should we collapse this process as they are equivalent, then we can redraft this entire system to look something like this. S of t going into a system, h of t, and here we have h hat of t giving us the output. Okay, then you can say, for instance, if that is the link there, then from this we can deduce that S of t convolve with h of t convolve with h hat of t is the same as S of t, such that this operation is what we have in red, right? So we already know intuitively, based on what we've done so far, S of t convolve with delta function, so unity value, will give us S of t. So following this, we can therefore deduce that the direct delta function, which is the unit impulse, is the same as h of t this is the same as h of t convolved with h hat of t. Okay, and then if we take the Laplace transform and the inverse Laplace transform, so we'll have h of s, then h hat of s. Here, the Laplace transform of the direct delta function gives us 1. Okay, so technically, can say that h hat of t is the same as the inverse of h of s. Now, in this case, h hat of t can be evaluated by taking the inverse transform of 1 over h of s. Okay, so this implies that the transform h of t is the reciprocal of the transform h hat of t. Okay, we may not be going into deconvolution in detail in this course, but you should note that deconvolution is very, very important and quite useful in image processing and some other application. Well, I want to believe this is a good place to stop. See you in our next class. Bye for now.